All right, in this video, I want to establish the power rule for derivatives. So, before we get into the power rule, let's look at a derivative problem. Let's find the derivative of, let's say 2x squared plus 1. And we'll use the definition of the derivative. Okay, so this is equal to the limit as delta x goes to 0 of 2 times, instead of 2x squared, it's 2x plus delta x squared plus 1 minus 2x squared plus 1 all divided by delta x. So we're using here the definition of the derivative, which is f prime of x is equal to the limit as delta x goes to 0 of f of x plus delta x minus f of x all divided by delta x. Okay, so we have to somehow eliminate this delta x in the denominator. So let's see if we could simplify the numerator and go from there. So we'll start with this, the x plus delta x squared. And we'll FOIL that out. We'll multiply x plus delta x times itself. So we have the limit as delta x goes to 0 of 2 times, well, x times x is x squared. And then we'll have x times delta x twice. So 2x delta x plus delta x squared. Then there's a plus 1. And we'll distribute that minus sign. So minus 2x squared and minus 1. And that's all over delta x. Or the limit as delta x goes to 0. So let's distribute the 2. So that's 2x squared plus 4x times delta x plus 2 times delta x squared plus 1 minus 2x squared minus 1. And that's all divided by delta x. Okay, we could cancel. We have a positive 2x squared and a minus 2x squared. We have a positive 1 and a minus 1. So now we're down to the limit as delta x goes to 0 of 4x times delta x plus 2 delta x squared over delta x. And we could factor out a delta x in the numerator. Both terms have a delta x, so we could factor out a delta x. We could cancel the delta x on the bottom. So that's the limit as delta x goes to 0 of delta x times 4x plus 2 delta x all divided by delta x. Okay, so we have a factor of delta x on top, delta x on the bottom. They cancel. So now we have the limit as delta x approaches 0 of 4x plus 2 delta x. So now we can substitute in 0 for delta x, since there's no longer a delta x in the denominator. And we have 4x plus 2 times 0, or 4x. So the derivative of 2x squared plus 1 is equal to 4x. Okay, so even with a with a function like this still takes a little bit of algebra. So what I want to do now is establish a rule for the derivative of x to a power. Okay, so that was just an example. So now what we want to do is we want to find the derivative of x to the power of n. X to the power of n. Okay, we'll approach this the same way as we did with the specific example. We'll apply the limit definition of the derivative. Okay, so that's the limit as delta x approaches 0 of, instead of x to the n, it's x plus delta x to the n. You know what? I'm going to erase that and write that in red. You'll see why in a moment. X plus delta x to the power of n minus x to the n all over delta x. Okay, so now we have this x plus delta x to the power of n. Well, we don't know what n is. N could be anything. So to evaluate this this part of the expression in red, we need the binomial theorem. And the binomial theorem, so this is something you would see in maybe a pre-calculus class. The binomial theorem tells us how to multiply out a binomial, a plus b. In this case, the a would be the x and the b would be the delta x. A plus b to the power of n. And the binomial theorem says that this, once we FOIL this out n times, this is equal to the sum as I goes from 1 to n of n combination I times a to the power of n minus I times b to the power of I. So the a, when, oh, sorry, not I equals 1, it's I equals 0. We need to start with 0. So when I is 0, we have a to the power of n and b to the power of 0. And then when I is 1, it's a to the n minus 1 and b to the 1. So what happens with successive terms in this expansion, the powers on a start at n and drop by 1 with each successive term. A to the n minus 1, a to the n minus 2, and so on. And the powers of b start at 0 and progress upward to b to the first, b to the second, up to b to the nth power. And another way of writing this n combination I, so there's a formula for this. So that's I goes from 0 to n of n factorial divided by n minus I factorial times I factorial times a to the n minus I, b to the I. Okay, and once we expand this, so this is a shorthand notation for a sum of terms where I is your variable and I starts with 0 and takes on every value from 0 up to n, every whole number value. So plug in 0 for I, then 1 for I, 2 for I, 3 for I, so on. And so what this is equal to is a to the n. So when I is equal to 0, this part, this first factor, the n combination I is equal to 1, because a to the n, plus n times a to the n minus 1 times b to the first power plus n combination 2. And then the powers on the a drop successively and the powers on the b increase successively. So that's a to the n minus 2, b to the second. And the last term in the sequence is b to the power of n. Okay, so we're going to apply this binomial formula. So x plus delta x to the power of n should be equal to x to the n plus n times x to the n minus 1, b, not b, b is delta x, times delta x to the first power plus n combination 2, x to the n minus 2, b to the 2. Again, I did it again, not b. It's delta x. All the way down to x to the 0 times delta x to the power of n. Okay, so this the result of the binomial theorem, let's make this a little bit smaller. This is what's going in here. Okay, so back to our limit. We have the limit as delta x approaches 0 of x plus delta x to the n. So that's x to the n plus nx to the n minus 1 delta x plus n combination 2 x to the n minus 2 delta x to the 2 all the way down to delta x to the n. And then we have this minus x to the n at in the second term in the numerator. So there's a minus x to the n all over delta x. Okay, so first term, x to the n. Last term, minus x to the n. They cancel. And every term now, once we've canceled that x to the n and minus x to the n, every term in the numerator has a delta x in it. So we could factor out a delta x. So we have the limit as delta x approaches 0 of delta x times n x to the n minus 1. There's no delta x here because this is delta x to the first power. We factor that out. Plus n combination 2 x to the n minus 2 times delta x all the way down to, now we're at delta x I'm not sure why that's a 0. Let's get rid of that 0. Down to delta x to the power of n minus 1. Okay. And this is all over delta x. All right, so now we have let's make this kind of big bracket so we know where it starts and where it ends. So we have a factor of delta x on top. We have a delta x on the bottom. They cancel. So we have the limit as delta x goes to 0 of nx to the power n minus 1 plus n combination 2 x to the n minus 2 times delta x plus n combination 3 x to the n minus 3, so on and so on, until we get down to delta x to the power n minus 1. Okay, a lot of algebra so far, and now we can apply the limit. Every delta x can now be replaced with a 0. And since, except for this first term, every term in this sequence of terms has a delta x in it. So if we plug in delta x, each one of these terms becomes 0, because it's something times 0, because delta x becomes 0. And we are now at the limit. As delta x goes to, well, actually, no, we've evaluated the limit. So this is simply n times x to the power n minus 1. And that's it. So after we've done some pretty complicated algebra, we've come up with the power rule for derivatives. The power rule for derivatives says that the derivative of x to the power of n is equal to n times x to the power n minus 1. This is a very, very important derivative rule. We're going to be using this as we go through a calculus course. We're going to use this probably hundreds of times. So there's 4 general derivative rules, and this is the first of those 4 rules. Rule number 1, power rule. Later we'll talk about the product rule, the quotient rule, and the chain rule. So those 3 with the power rule make up the 4 general derivative rules. Okay, so what I want to do is go back. What I want to do is to go back to this original problem, the derivative of 2x squared plus 1. Well, the derivative of 2x squared plus 1, according to the power rule, well, 1 is the same as x to the 0 power. So we could actually write, this is the derivative of 2x to the 2nd power plus x to the 0 power. And the power rule says, well, basically what's going on here is with the derivative of x to a power, the power pops out front. So the n comes out front and then decreases by 1. The power goes out front and decreases by 1. So this 2 pops out front. 2 times 2 is 4. Let's go back to black. 2 times 2 is 4. The power pops out front and decreases by 1. So that's 2 times 2 is 4. And we have x to the 1st power. And then here, the 0 pops out front times x to the negative 1 power. But 0 times anything is 0. So we get simply 4x. And, you know, probably we don't have to actually do this part here with the x to the 0, because we most likely you've already encountered the constant rule. So the derivative of a constant is equal to 0. So we could go directly from here. Actually, we could go directly to here to 4x plus 0 or 4x. So now that we've established the power rule, this first problem, which took us a few minutes to do, this whole process is reduced to just a couple of seconds of work. Power pops out front and decreases by 1. And that's it. That is the power rule. Power pops out front and drops by 1. All right. So that's it for the power rule. Let's do a couple of examples. Let's say the derivative of, well, let's switch notation. Let's say f of x is equal to 8x plus 4 over x cubed. Now let's say g of x is equal to 3x squared plus the square root of x, all divided by x. Let's actually go one more h of x is equal to, let's say, x to the 4th power times 2x squared minus 5x. Okay, so we want to find the derivative of each of these three functions. So we have the power rule. So the first thing, so let's look at the f function. The first thing we have to do is rewrite the function so it aligns with or matches up with the power rule. So we could say f of x is equal to 8x to the 1st power plus, well, x to the 3rd on the bottom becomes x to the negative 3rd on top. So that's 4x to the negative 3rd power. So now we can apply the power rule. Derivative of the f function is equal to power pops out front. So the 1 pops out front. So 1 times 8 is 8. And then the power drops by 1. So that becomes 8x to the 0 power. 8x to the 0 power. And then for the second term, the minus 3 pops out front. So minus 3 times 4 is a minus 12. X to the negative 4 power. So when we simplify this, x to the 0 is 1, so that's 8. And if we want to get rid of this negative exponent, that's minus 12 over x to the 4th power. So that would be the derivative of f of x. Now for the g of x function, so we can't just use the power rule term by term. So you look at g of x and h of x. In g of x, we have a quotient, and h of x, we have a product. We'll establish derivative rules later for quotients and products. But right now, we could just take the derivative of individual terms that are some multiple of x raised to a power. So what we could do here is we can split this g of x up into two fractions. So 3x squared over x, and instead of the square root, I'm going to use x to the 1/2 power. That's the same as the square root. It just looks more like the power rule. And now, the first term, one of the x's on top, will cancel that x on the bottom, so that becomes 3x. And here, x to the 1/2, x to the 1st, we subtract exponents, so that's x to the negative 1/2 power. So we've done a little bit of algebra to rewrite, and we're doing the same thing in all three of these problems. Rewrite the function so it looks like x to a power, x to a power. Now we can take the derivative using the power rule. So that's 3x to the 1st power. So 1 comes out front, 3 times 1 is 3, and then the power drops by 1. And then for the second term, the negative half comes out front and then drops by 1. So we're down to negative 3 over 2. So again, x to the 0 is 1, so that's 3. That'll be a minus. And we can move this negative exponent to the bottom of the fraction, so that's 1 over x to the 3/2 power. All right, looks good. And so finally, h of x. Again, we have a product here, so we can't just ignore the parentheses and take the derivative of x to the 4th. It doesn't work that way. We need individual terms where each term looks like a multiple of x to a power. So what we could do is we can multiply through the x to the 4th. So h of x would be x to the 4th times 2x to the 2nd. So that's 2x to the 6th power minus x to the fourth times the 5x. So that's a minus 5x to the fifth power. So now it is in the correct form to apply the power rule. So the derivative is equal to power comes out front. 6 times 2 is 12. Drops by 1. Minus power comes out front. 5 times 5 is 25. Drops by 1. And that's it for the derivative of h of x. Just h of x by itself, that would be sort of like a full page problem. Maybe take us 6, 7, 8, maybe 10 minutes if we were using the limit definition. But our goal here, moving forward, is to use the limit definition of the derivative as little as possible. We want to establish these derivative rules that are quicker and easier and more efficient, that sort of streamline our calculations. Okay, so that does it for our discussion on the power rule. Next, we'll talk about the next three really important rules. So let me just real quick before we go. 1, power rule. 2, product rule. 3, quotient rule. And 4, the chain rule. So we've discussed the power rule and the next 3 to come. So we have these 4 derivative rules we're going to be using very, very often, all 4 of them. Throughout all of Calculus 1, we're going to be using these 4 rules. Okay, that does it for the power rule.